Hello everyone, welcome to the course Network Analysis and Transmission Line. In last class, we discussed steady state and transient analysis, introduction part, and initial conditions of the inductors, capacitors, and resistors. Now, today we are going to start actual concept, the transient analysis or response of series RL circuit. Consider a series RL circuit having resistor and inductor. A switch S is connected here, and the switching action takes place at t equal to 0. Initially the switch S is open and it will be closed at t equal to 0, and we are connecting one DC source V, and here we are going to discuss the transient analysis of the series RL circuit for DC excitations. Now when switch S is closed at t equal to 0, that we can say transition takes place, means before switch S is closed, at t equal to 0 minus switch S is open. Now we are changing the condition of the circuit at t equal to 0 by closing the switch, means at t equal to 0 plus just immediately after closing the switch, and we can expect certain current I of t during certain interval t greater than 0. Now we have to study the behavior of the RL circuit after switch S is closed. So at t equal to 0 minus switch S is kept open. So at t equal to 0 minus switch S is kept open. That's why we know that the initial behavior of the inductor is I of 0 minus is equal to 0. This is one of the important criteria. So at t equal to 0 plus switch S is closed. At t equal to 0 switch S is closed. T equal to 0 plus is nothing but instant at which switch S is just closed. At that condition also we know that the current in the circuit is 0. Why? Because the inductor does not allow sudden changes in the current. Now we have to study the behavior of the circuit at t greater than 0. Now let us follow the KVL. V equal to, we know that VR plus VL, and applied voltage V equal to, we know that the voltage across resistor equal to I of R into I of t plus L into d I of t by dt. And if you rearrange this equation, d into I of t by dt plus R by L into I of t is equal to V by L. Now we know that it is in the form of dy by dx plus py equal to q form. We know that if at all any one of the equation is in the form of this equation, y equal to q by p plus k into e power minus px. This is the solution. In last class we discussed this concept. Now what is the mathematical equation we got after rearranging? Di of t by dt plus r by l into I of t is equal to v by l, where this is nothing but q and p, this is nothing but q. Now we can get the solution of the non-homogeneous equation. I of t equal to v by r plus k into e power minus r by l into t. Let us assume this is the equation 1. Now here k is the constant. Here we have to calculate the k based on the initial conditions. So we know that at t equal to 0 minus I of 0 minus is equal to 0. Now substitute these conditions in the equation. I of 0 minus is equal to v by r plus k into e power minus r by l into 0. So we know that e power minus 0 value is 0. That's why I of 0 minus is equal to V by R plus K. So we know that I of 0 minus equal to 0. So V by R plus K. That's why we got K equal to minus V by R. So this is a way to find the initial conditions. Now if you apply this equation, the equation 1, we will get the complete solution I of t equal to V by R plus K value is minus V by R e power minus R by L into t. So at the end we got the final solution I of t equal to V by R, if you make common, 1 minus e power minus R by L into t. So this is the current response of the series RL circuit. Now let us see the different stages of this equation by taking the t equal to 0 instant and t equal to infinity instant across resistors and inductors. Now we got the equation I of t is equal to V by R into 1 minus e power minus R by L into t. Let us take down a t equal to 0 minus I of 0 minus is equal to V by R into 1 minus e power minus 0. We know that e power minus 0 is 1, 1 minus 1 0. So I of 0 minus is 0. So we said theoretically before closing the switch current is 0. Now we got mathematically before closing switch current is 0. At t equal to infinity, I of t is dash. I of t is equal to V by R into 1 minus e power minus R by L into infinity. We know that e power minus infinity is 0. So we got I of t equal to V by R. If you see the circuit, at t equal to 0 switch S is closed and we are taking it long run, we have the circuit resistor is resistor, and we know that at the steady state condition inductor acts as a short circuit. If at all inductor is short circuit, for the given voltage the current I equal to V by R. So this is the solution. Mathematically we got I equal to V by R, and theoretically based on the analysis at steady state condition inductor acts as a short circuit. That's why the current is inductor acts as short circuit, current I equal to V by R. Now we got these two conditions. So if you place these two conditions in the graph, and before that, if at all we have take the t equal to certain value that is equal to L by R, then what will be the mathematical equation? So what is the current at t equal to L by R? T equal to L by R, I of t is equal to V by R into 1 minus e power minus 1. So if you solve this equation, you will get 0.632 times of V by R. Means, so what is this t equal to L by R? This we can call it as a time constant tau, that is equal to L by R. Means the value of the time at which the current in the circuit reaches to 63.2% of the actual voltage. So if you place all these concepts in the graph with respect to t, and this is the I of t. So initially at t equal to 0 the current is 0. At t equal to infinity, current reaches to the maximum state that we can call as a V by R. Here we cannot take infinity at steady state condition, and at particular time some tau that is equal to L by R, the current is reaches to 0.632 times, means the graph will be exponentially growing. So at particular time the current is 0.632 times of V by R. This condition, this time constant is nothing but the current in the circuit, time taken by the circuit to reach into 63.2% of the maximum current. So this is the way one can solve the given series RL circuit based on by using the non-homogeneous mathematical equation and initial conditions. First we are applying the KVL. Before that we are finding initial conditions, then apply the KVL and use the non-homogeneous equation solutions and get the K value and take the analysis at t equal to 0 and t equal to infinity cases.